Imagine a world where everything can be explained, from the smallest particles to the vastest galaxies. Welcome to the realm of physics. A realm not dictated by whims and fancies, but by laws and principles. A realm where reality is not just perceived, but understood. Physics, in its essence, is a natural science. Like a master key, it unlocks the mysteries of the universe, providing answers to questions that have confounded humanity for centuries. It is a vast and complex field encompassing a range of topics from subatomic particles to black holes, from the behavior of basic elements to the intricacies of the universe. At its core, physics is the study of matter and its interaction with energy. It delves into the nature of the universe, providing a framework to comprehend the world around us. It's a science that observes, analyzes, and builds models to explain how matter moves through space and time. It's a science that explores the fundamental elements of the universe, the smallest building blocks of life, and the forces that bind them together. But physics is not just about matter and energy, it's also about understanding the forces that govern the universe. Forces like gravity that keep our feet planted firmly on the ground, or electromagnetism that powers our technology, or nuclear forces that fuel the stars. It's about understanding how these forces interact with matter, shaping the universe and everything within it. Physics is a journey, a quest for knowledge. It's a path that leads us to understand the very fabric of reality. It's a journey filled with awe and wonder as we explore the grandeur of the cosmos and the subtlety of the quantum world. It's a journey that pushes our understanding to its limits, challenging our perceptions and reshaping our worldview. Now that we have a general understanding of what physics is, let's delve deeper into its fascinating concepts. From the fundamental particles that make up matter to the awe-inspiring phenomena of the cosmos, join us as we unravel the mysteries of the universe, one physical law at a time. Let's start from the basics, the foundation of everything around us, atoms and particles. It's an understatement to say, atoms are important. They are, in fact, the very building blocks that construct everything in the universe, from the screen you're watching this on, to the air you breathe, to the farthest star in the distant cosmos. Atoms themselves are tiny worlds bustling with activity. They consist of even smaller components known as subatomic particles. The three most well-known of these particles are protons, neutrons, and electrons. Protons and neutrons huddle together to form the atom's nucleus, a dense core at the center of the atom. Surrounding this core, electrons zip around in a cloud of buzzing energy. Think of it like a miniature solar system, with the nucleus as the sun and electrons as the orbiting planets. Each of these subatomic particles plays a crucial role. Protons, positively charged, and neutrons, neutrally charged, give the atom its mass. Electrons, with their negative charge, determine the atom's size and how it interacts with other atoms. Basically, they're the social butterflies of the atomic world. But our understanding doesn't stop there. Science has delved even deeper, revealing that protons and neutrons are not the smallest players on the field. They themselves are composed of even tinier particles known as quarks. It's a bit like Russian nesting dolls, but with particles. So why does this matter? Why do we care about these infinitesimally small particles? Well, understanding the structure of atoms and their subatomic particles helps us understand how the universe works on a fundamental level. It's the key to unlocking the secrets of matter, energy, space, and time. Physics is, after all, the study of how the universe behaves. And to understand the universe, we must first understand its building blocks. From the tiniest quark to the largest galaxy, everything is interconnected in this vast, beautiful cosmic ballet. Just as atoms are the building blocks of the universe, they are also the building blocks of physics. Now, we move on to the laws that govern the motion of objects in our everyday world. Welcome to the world of Newton and classical physics. Let's journey back to the 17th century, where Sir Isaac Newton formulated three laws that would become the cornerstone of classical physics. The laws of motion that describe the relationship between a body and the forces acting upon it, and its motion in response to those forces. The first law, often referred to as the law of inertia, states that an object at rest will stay at rest, and an object in motion will stay in motion, unless acted upon by an external force. This means, for example, that if you slide a book on a table, it will eventually stop because of the frictional force between the book and the table. Newton's second law introduces us to the concept of force. It tells us that the force acting on an object is equal to the mass of that object times its acceleration. Simply put, if you push a heavy object, it moves slower than if you push a lighter one with the same force. The third law, often summarized as, for every action there is an equal and opposite reaction, explains why you move backwards when you jump off a boat. The force you exert on the boat propels it in the opposite direction. These laws form the foundation of classical physics, a framework that describes the motion of macroscopic objects, from apples falling from trees to planets orbiting the sun. It's a wonderful, predictable world where time and space are absolute. But the world of physics is a rabbit hole that goes much deeper. As we journey into the microcosm of atoms and particles, or reach out to the vastness of galaxies and black holes, we find that Newton's laws start to falter. Newton's laws are the backbone of classical physics, but as we delve deeper into the universe, we realize that these laws cannot explain everything. When we zoom into the world of atoms and subatomic particles, classical physics fails, and here comes quantum physics. Quantum physics, also known as quantum mechanics, is a branch of physics that deals with phenomena on a very small scale, such as molecules, atoms, and subatomic particles. It's like stepping into an entirely different universe, where the rules of classical physics no longer apply. You see, in the realm of the very small, things start to behave quite peculiarly. Particles can exist in multiple places at once thanks to a principle known as superposition. Imagine being in your kitchen and your living room at the same time. Sounds impossible, right? But that's the reality for particles in the quantum world. And then there's the uncertainty principle, proposed by Werner Heisenberg. This principle states that you can't simultaneously know both the precise location and the speed of a particle. It's as if the more you know about where a particle is, the less you know about how fast it's moving, and vice versa. These principles contrast sharply with classical physics. In the macro world, an object's position and speed can be measured simultaneously. And objects certainly can't be in two places at once. But in the quantum world, these strange behaviors are the norm. Quantum physics also introduces the concept of wave-particle duality. This means that particles like electrons and photons behave as both particles and waves. The light from your lamp? It's both a stream of particles and a wave of energy. But how can this be? How can something be both a wave and a particle? Well, that's one of the many mysteries that quantum physics presents. Even Albert Einstein was unsettled by the strange and unpredictable nature of quantum mechanics, famously saying, "God does not play dice with the universe." Quantum physics may seem strange and counterintuitive, but it's the theory that best explains the behavior of the tiniest particles in the universe. Despite its peculiarities, it's an essential part of our understanding of the physical world, and it's the foundation for technologies like lasers, semiconductors, and even the computer you're using right now. Now let's move from the very small to the very big, from particles to galaxies, as we explore the theory of relativity and the Big Bang theory. Enter Albert Einstein. In the early 20th century, he proposed a revolutionary idea, the theory of relativity. This theory merged the concepts of space and time into a four-dimensional structure known as space-time. It suggests that nothing in the universe can travel faster than light, and time slows down as we approach light speed. Quite a twist, isn't it? Einstein's theory also predicts the existence of black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape. These black holes, along with the expansion of the universe, are some of the most profound implications of the theory of relativity. Now, let's take a leap back, around 13.8 billion years to be precise. This is where the Big Bang theory comes in. According to this theory, the universe began as a hot, dense point nearly infinitely small. Then, it expanded rapidly in a hot fireball of particles and radiation. Over time, the universe cooled and matter formed, allowing for the creation of atoms, stars, galaxies, and eventually life as we know it. This theory, supported by a wealth of observational evidence, is our best explanation for the origin of the universe. But remember, theories in physics are not set in stone. They are constantly questioned, tested, and refined. That's the beauty of this field. It thrives on curiosity, on the relentless pursuit of understanding the fundamental laws that govern our universe. From the smallest particles to the vastest galaxies, physics provides us with the tools to understand the universe. So next time you marvel at the night sky or contemplate the complexity of your own existence, remember, it's all part of the grand tapestry of physics.